have Professor Sudhir Ghorpade from Indian Institute of Technology, Bombay, and his research topics are mainly algebraic geometry, combinatorics, coding theory, commutative algebra. And today he will talk about some of his research topics. Welcome, Professor Sudhir.
Good morning. So, first of all, thank you for having me. Is there an echo?
Yeah, there is some echo.
Should I reduce the volume? Maybe, just let me put it away. Okay. Oh. Okay, so I exist. Yeah. Thank you. So, as I was saying, okay. If need be, we can live with it. I mean, there are people who like the sound of their own voice more than anything else. Not exactly one of them, but it could be an experience. Okay. 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 I think this is better, right? Okay. Still some echo, but all right. Sorry about this echo, but we can live with it if you don't mind and people online don't mind. But it's a pleasure to be here. I was supposed to meet Raphael many years ago in Canada. Somehow that didn't happen, and I'm very glad I'm seeing him here in Mexico City. So the topic I'm going to talk about, it sort of has some Mexico connection. If there is time, I can mention that or tell you over a coffee. I have planned this talk in such a way that I sort of start from scratch. I don't speak Spanish. Maybe I have a funny accent. So feel free to stop and ask questions. And the experts, I know there are experts in the audience, so they can excuse me for being a little bit slow, at least in the beginning. So let's get started. There's also one typo in the title, which I just realized when I was sitting here. There's not much I can do about it, but it's an exercise what that typo is. Okay, let's see. Okay. So let me start with a quick introduction to what are called Grassmannians or Grassmann varieties, which is among the most basic objects minus 1, exactly that. And now if you take a subspace here, sorry, W, maybe I should be away from that. Then, slightly better, I don't know. Then you just pick a basis, so there are L elements in a basis, and you simply map a subspace spanned by W1 to WL to the class in the projective space of this wedge product W1 wedge W2 wedge WL. Okay, so in this way, this would sit inside that. Notice that if you were to take another basis instead of W1 to WL, say W'1 to W'L, you would get a different element here, but the two wedge products would differ from each other by a non-zero constant, which is exactly the determinant of change of basis matrix. So as an element of the projective space, it's well defined. It's independent of the choice of basis. And as I was just saying, if L equal to 1, this is just the projective space of M minus 1 dimension. If you want to be a little bit more explicit, what you can do is, well, you have your V, so you can fix some basis of V, let's say E1 to EM, which means each one of these guys, W1 to WL, would be row vector of length M, because you write it as a linear combination of this E1 to EM. So this would give rise to a matrix whose rows are coordinates of this basis. So first row is W1, second row is W2, Lth row is WL. So you think of it as a L cross M matrix. And now what I do is, from that L cross M matrix, I just take all L cross L minors. So if I have a L cross M matrix, how would a minor look like? Oops, something like that. So you just have to pick up L columns. And let's say I pick up columns indexed by alpha 1, alpha 2, alpha L, and then I get a square sub matrix, and I take its determinant, and I can do it for any collection of these choices of columns, and obviously there are M choose L ways of doing that, and so that gives me a M choose L vector, and that would, up to non-zero multiplication by non-zero constant, you look at the corresponding point. And that's exactly what this is. That's a sort of more concrete way. So these are sometimes called the Plucker coordinates of the corresponding to the element W, okay? And in terms of matrices, if I were to pick another basis, then this matrix would change to something with this matrix A sub W multiplied on the left by L cross L non-singular matrix. But when you take the L cross L minors, all of them would be multiples by the determinant of that L cross L non-singular matrix. So up to multiplication by non-zero constant, or up as a point of projective space, it's completely well defined, okay? Moreover, so this sits inside this space in this manner, and the map is actually an injective, it's an embedding. Then it's natural to ask, does it constitute all of this projective space? Of course, if L equal to 1, this is not just injective but also surjective. In general, it is not surjective, but it sits inside this projective space as a geometric object. That means it's given by zeros of bunch of homogeneous polynomials. In fact, homogeneous polynomials of degree 2, quadratic homogeneous polynomials. So, oops, okay. So, so as such, it's a projective algebraic variety given by common zeros of certain actually pretty explicit set of quadratic homogeneous polynomial in M choose L variables. And as a projective algebraic variety, it is non-degenerate. What does that mean? That means it does not sit inside a hyperplane in Pk minus 1. So K minus 1 is the correct dimension of the projective space in which it sits. It is irreducible, it is smooth, and it is rational. The rational would mean that the function field is a purely transcendental extension of the ground field F. Okay. Another way to think about the Grassmannian is you have the space of all L dimensional subspaces of V. So there is a natural action of GLM on that. Let's see how do we do this. Yeah, oops. So GLM acts naturally, and in fact this is clearly a transitive action. It will M cross M non-singular matrix or an invertible linear map from V to V would transform an L dimensional subspace to another L dimensional subspace. This is a transitive action, which means just one orbit, which means if you look at the orbit, which is all of the Grassmannian, then you can think of it as a quotient of the general linear group modulo a stabilizer of any fixed element. Okay, so that stabilizer is what is called a parabolic subgroup, in fact a maximal parabolic subgroup. And so you can think of the Grassmannian as this homogeneous space of GLM modulo this parabolic subgroup. Okay, this already indicates to you that it's a non-singular variety because any point is like any other point. It's a homogeneous space. If you are over a classical field like real numbers or complex numbers, then this smooth variety you can think of it as a manifold, a real manifold or a complex manifold. And we understand the topology very well. It's a very classical object also in topology. So we know the cohomology spaces and the Betti numbers. In fact, it turns out that the odd dimensional cohomology, when you think of it as a complex manifold, is 0, whereas the even ones that survive, and you know the dimension of that in many different combinatorial ways. For example, the dimension of the 2-Newth cohomological space, I'm denoting it by B sub nu, B for Betti, is precisely the number of partitions of nu into at most L parts, each part at most M minus L. Or there are interpretation in terms of non-intersecting lattice parts and so on and so forth, if you know what those are. Anyway, so point I'm trying to make is a very nice object. You know a lot about it, very nice geometrically, algebraically, and topologically, okay? The case that I'm interested in is the one, let's see, oops, yeah, here. Now let's suppose my base field is finite. If the base field is finite, then of course as a set or the set of FQ rational points is a finite set. And whenever you see a finite set, and if you're a combinatorialist, you want to give a nice formula for the cardinality. And this is something which is known at least since Gauss. So the number of L-dimensional subspaces of an M-dimensional vector space over FQ is actually what is called the Gaussian binomial coefficient. I denote it like this, and explicitly it is this. And this is an easy exercise because you just need to see if you look at the numerator, it's the number of L tuples of linearly independent set, say W1 to WL, which would span the first one, you can exclude 0, second one you exclude the multiple of the first one, third one you exclude the linear combination of the first two and so on. But then different tuples would give rise to the same subspace that amounts to multiplication on the left by L cross L non-singular matrix, and the rows of that you could choose it in this way, exactly the same argument. So that more or less proves that the cardinality is given by this formula, which looks like a rational function, okay? So it's a rational function in Q, but in fact, as you can very well see, there is a lot of cancellation, okay? And this rational function is actually a polynomial. And one of the remarkable facts that this is a polynomial in Q, whose degree is exactly L times M minus L. This is a number which will come up again and again. I'll denote it by delta. And the coefficients of that are the Betti numbers that I showed you in the previous slide. So there's this beautiful connection between the, if you like, the arithmetic or combinatorics of this variety with the topological thing. I should mention in passing that this was one of the original motivations for Andre Weil to make his famous conjectures, where he, this Riemann hypothesis over finite fields and so on and so forth. And, anyway, so you know the coefficients, and those are exactly those non-negative integers which have topological and combinatorial interpretation mentioned. If you are teaching calculus, you could give an exercise to your students to calculate the limit of this as Q goes to 1. And that's a nice calculus exercise. And if they did it correctly, you will get the limit as the ordinary binomial coefficient. That also explains why it's like a binomial coefficient, okay? Very good. So, oh yeah, no. So now let me introduce you to another very classical object, and these are the Schubert varieties. So I told you what is Grassmannian. Now let's talk about Schubert varieties. So as I was saying earlier, let's fix a basis, let's say E1 to EM of V, and any alpha in my indexing set. What does that mean? That means alpha is an L tuple of positive integers strictly increasing between 1 and M. Equivalently, this is the number of, this is like a L element subset of 1 to M. Okay, and the cardinality of this indexing set is obviously M choose L. So for a fixed alpha, you can define the corresponding Schubert variety as follows. What you can do is you take, so you have your V, maybe think of it as F to the M, and inside you just take some, I fixed a basis, right? So there is what is sometimes called a full flag, and maybe I have a AI here, and this is just the span of the first I basis elements. So A1, A2, and what you can do is, let me see if I've used the same notation. No, I'm sorry. I did not. Okay. Maybe I'm just taking a partial flag. Oops. So I'm looking at A1 containing A2, okay, AI, let us say, AL, where AI is the span of the first alpha I fixed basis vector. So AI is a alpha I dimensional space. So what you do is you require your subspace W to intersect A1 So it turns out that in the Schubert variety, the piece of beta where beta is not less than or equal to alpha would be 0. In fact, the Schubert variety is the intersection of the Grassmannian with those Plucker coordinate hyperplanes corresponding to p beta for which beta is not less equal. But, okay, and this is actually a concrete incarnation of what is called the Bruha order or Bruha-Chevalier order. If you're thinking in terms of, the algebraic group approach I mentioned. Okay. Very good. So, so now I want to look at some little bit more involved. So I have the Grassmannian inside pk minus 1 sitting non-degenerately, or more generally, okay, maybe I should say make one remark that if my alpha is sort of the maximum possible maximal element in this order. What would be the maximal element? You just take the last guy to be the biggest it can be, which is m, and the one before that is the biggest it can be, which would be m minus 1. And if you keep doing that, the first one would be m minus l plus 1. So the consecutive sequence of L integers ending in M, then you will see that this condition is no condition at all. And so then the omega alpha is all of the Grassmannian. In other words, if I'm studying Schubert varieties, Grassmannians are a special case. Okay, very good. So let's and also another remark. I think I said it here. When you take this correct K alpha, then this is a non-degenerate embedding. This also doesn't sit inside hyperplane. Okay. So now what you do is you look at this non-degenerate embedding of the Schubert in the correct projective space, in particular Grassmannian in the correct projective Plucker projective space, and you take a hyperplane inside this. Okay. Now this is not going to sit inside that hyperplane, so you intersect the Schubert variety with that hyperplane. And you're sort of interested in the question is that, so you look at this hyperplane section, and what is the maximal hyperplane section? That's sort of the question. And so in other words, and this maximal you can interpret in many ways. I'm going to be interested in the interpretation when I look at the FQ rational points, just work over finite field FQ, and then I can count how many points are there in this intersection, and I like to maximize this number. So I'll denote it by E sub alpha L. It's the maximum possible cardinality of the hyperplane sections of the Schubert variety. omega alpha. And once I would like to find that, and I would also like to find what are the hyperplanes for which the maximum is attained. So that is this number. Okay, and the maximum is over hyperplanes in this projective space. And you could do a little bit more general. You could, instead of hyperplane, which are like codimension 1 linear subvarieties of this, you could take codimension 2, codimension 3, and so on. In general, you could cut with the codimension R linear subvarieties of this projective space and ask for this maximum here and the corresponding linear subvarieties of codimension R which attain that maximum. So that's a more general version of this question. Okay, and these questions are actually open in general, and they can in fact be of interest to even geometers, but it turns out that they are very interesting also for coding theory. And so I want to explain that. So I know that there are experts here, but I'll just start with the quick review of coding theory and then relate these questions to that. Okay. Yeah, coding. The theory of linear error correcting codes. Okay. Okay. So what is coding theory? So here is a 2-minute crash course on coding theory. So for me, all codes are going to be linear codes. So I will look at what is called an NKQ code, which is sometimes called a linear code of length n, dimension k over the finite field fq, or QRE linear code. And that is simply defined as a k-dimensional subspace of this specific n-dimensional vector space over fq to the power n, which is like an n-dimensional vector space with a fixed basis, and you take a subspace of that. Okay, and inside this ambient space, you have the notion of Hamming weight, and the Hamming weight of an element here is simply defined as the number of positions in which you have a non-zero coordinate. And more generally, this is for an element. More generally, you can also define it for a subset or a subspace. Subcode just means a subspace of C as the number of those positions for which there is somebody in the subset D with a non-zero coordinate in that position. If you think about it, this is like the cardinality of the union of the supports of every element C in D. Okay, and what people want to do many times is you want to look at some codes where you look at the Hamming weights of its elements of that subspace. Of course, you don't take 0 because 0 will obviously have weight 0, but other than 0, and you want to minimize this number, and that's called the minimum distance of a code. And many times you want to sort of create a subspace for which this minimum distance is large. If you think of this room as a 3-dimensional space, but with the axis only taking finitely many coordinates, you sort of want to fill it with points in such a way that those collection of points form a subspace, maybe a 2-dimensional subspace, or if you're able to think of an n-dimensional space, then a k-dimensional subspace, but in such a way that the points are as far apart from each other as possible in terms of this Hamming distance or Hamming weight. Okay, because minimizing this Hamming weight for a linear code is same thing as minimizing the Hamming distance, which is simply the difference of the Hamming weight of the difference between two distinct points. So that's called the minimum distance. And that's like a metric. There is a more general parameter called the generalized Hamming weight, or sometimes called the higher weight, and that's defined as rth generalized Hamming weight of a code is the minimum of the support weight of a r-dimensional subcode of C. Okay, so if r is equal to 1, if you think about it, if D is a 1-dimensional subspace, then the Hamming weight is really the Hamming weight of any non-zero element in it. So if you are kind of doing this minimum over R, for r equal to 1, you get nothing but the minimum distance. But in general, if r is equal to 2, 3, you would get numbers which are larger than the minimum distance. So, so this is sometimes called the weight hierarchy. And obviously r can take values from 1 to the dimension of C, which is k. So you want to kind of find dr for r going from 1 to k. And in coding theory, you would call a code to be non-degenerate, because you see these definitions are very much coordinate dependent if your C is not contained in a coordinate hyperplane of FQ to the n. Okay, and just I introduce one more notion called the dual of a code, and the dual of a code is just a set of those elements in the ambient space FQ to the power n for which the usual dot product with every code word, every element of C is 0. This x dot C is simply summation xi ci. Okay, so and of course, this usual dot product, there's no sense of saying it is positive definite. Nonetheless, it is a fact that this dual has complementary dimension. That means this is a space of dimension n minus k. But it can happen that this is also equal to C. In other words, C intersection C perf need not be 0 when you are over a finite field. Okay, so let's continue. So what's a good code? I mean, this is a rhetorical question or hypothetical question. This really doesn't have a good answer. Many a times I think of this question, I think I may have said this before, as to what is a good wife or what is a good husband? Let us say, what is a good husband? I don't know if there are ladies, they can specify. I mean, they'll say, okay, he should be handsome, he should be rich, he should be, he should help in the, he should be a good cook, maybe help with the family, then he should not look at any other woman, and so on and so forth. And you see that these requirements you can list down, and they're sort of mutually, sometimes they're conflicting. For example, if person satisfies all these properties, maybe he would look at somebody else or so. I don't know. So this is, the good code is a little bit like that. So I just list down some of the nice desirable properties for a code to be a good code. So as I was saying, you want to construct these subspaces in such a way that the minimum distance is pretty large. Obviously large vis-a-vis the length n. Yeah, another way to put it is that what is called the relative distance d over n should be as close to 1 as maybe possible. But at the same time, I mean, you could do this. For example, you could just take a subcode generated by all one vector, but then the dimension is very small and the minimum distance is n. So this is actually 1. So then you can't have a code of pretty large dimension. So you also want k to be large vis-a-vis n, which means this what is called the rate of k over n should be close to 1. Then I'm not going to explain it too much, but C should admit what is called good encoding and decoding. And then maybe you can say, well, we should not only know the minimum distance, but you should know all the generalized Hamming weights. Okay. Then there is something called automorphism group of a code, which is kind of like the set of symmetries of the code, the transformation which preserves the code. And many times it's a nice and challenging problem to find the automorphism group, and you would like it that you know all these symmetries, and there should be large number of symmetries. That usually helps in decoding. Then there is something called the spectrum. Spectrum is a bit like a horoscope of a code, where what does that mean? That means it's just for every, so the Hamming weight of an element here is some number between 0 and n. So you should know how many code words do I have of a given weight I, for I going from 0 to n. You can often write it in the language of a polynomial called the weight enumerator polynomial, so you want to know the weight enumerator. Then relatively recently people like this code to be what is called an LDPC code, which sort of means that the dual minimum distance should be small, and maybe the minimum weight code words of the dual generate the dual. For those of you who know coding theory, what would that mean is, you see, if the dual minimum distance is small and the minimum, let's say the dual minimum distance is 3, then, and you take the code words of that minimum distance 3, then you write down a matrix which a basis of this minimum weight code words of C prime, then you have a parity check matrix that they generate a matrix called the parity check matrix. So what you're saying is that your parity check matrix is very sparse. That will allow you to check very quickly whether something is a code word or not. I mean, this sort of goes to the, so, and so on and so forth. So these are some of the requirements, and just like requirements for a good spouse, some of these are conflicting with each other. Maybe you try to satisfy one, the other fails and so on. Yeah? Okay. But you do the best you can, just like in life. So what do you do? So I want to propose to you this code. It's not new, it's pretty classical. So let's look at the Grassmannian of L planes in M space over finite field FQ. This sits inside this projective space or the Schubert variety. And let me look at the evaluation map. So this sits inside this wedge L of V, and the dual of that is wedge M minus L of V, which is roughly speaking corresponds to hyperplane here. And you can look at, so this is another way to think of the Grassmann code or the Schubert code. You look at this evaluation map, which takes an element in the dual and simply evaluates it in the following way. What you do is you take fixed representatives of this FQ rational points of the Schubert variety inside this, because your Schubert variety sits inside Grassmannian, which sits inside this Plucker projective, and there are only finitely many points, let's say n alpha of them. And so these are elements of weight LV. This is an element of weight m minus LV. So if I take a typical element F here, weight it with this guy, then I will get something in weight MV. Remember, V was m dimensional. And so if weight MV is basically like a scalar when you fix a basis of V. So you get a scalar tuple. It's a point of FQ to the power n alpha. And this evaluation map is clearly injective. I'm sorry, not injective, but this is clearly linear. And so the image of that would be some subspace of FQ to the power n alpha. And that image is exactly a linear code, which I will denote it by C sub alpha of LM and called the Schubert code. And I was saying that if alpha I take it to be the maximum element in the Bruch order, you get the so-called Grassmann code. So this is, I'll drop the alpha in that case and just denote it by C. In the case of Grassmann code, it turns out that the evaluation map is actually injective, which means that the image will have the same dimension as this domain, which is m choose m minus L, which is same as m choose L. So I'll get a code of dimension m choose L. And what is the length of that? The length of that would be the number of FQ rational points of the Grassmannian. So that would be the Gaussian binomial. Okay? And it turns out that here, if I'm interested in the minimum distance of this Grassmann code, that corresponds exactly to the maximal hyperplane sections. So remember this quantity E sub alpha. In fact, that is true in general. The minimum distance of the Schubert code would be the length of the Schubert code minus the maximum number of points on a hyperplane section of the Schubert variety inside this non-degenerate projective space. And so that would be the minimum distance, and the number of minimum weight code word would be the number of hyperplanes which achieve that maximum. So those are the quantities I introduced earlier. Okay. As I said, if you have questions, feel free to stop and ask. Maybe I'm a little bit slow, but it's okay. And more generally, it's not just the minimum distance, but you can the generalized Hamming weights D sub R, they would correspond to maximal linear sections by a linear subvariety of fixed codimension R, and etc. Okay, and this will correspond to the number of minimal subcodes of dimension R. Okay, now the first remarkable result in this direction, in the general case of Grassmann code, was proved by this Russian mathematician called Dmitry Nogin, and he proved that the minimum distance of the Grassmann code is given by q to the power delta. So if you remember what delta was, okay, maybe I should write it. So delta was L times m minus L, and k was m choose L. So, and if you remember, the length was the Gaussian binomial, and if you I wrote down a formula for them, and that is Gaussian binomial is actually a polynomial in q of degree delta, and with a leading coefficient 1, a monic polynomial. In other words, asymptotically, your minimum distance is of the same order as the length. Okay, so that's, at least for large q, it is pretty large. And he also characterized the minimum weight code words. They correspond, it turns out, to the decomposable elements of this domain space, which m minus L. V. Okay, so which amounts to, another way of saying that is that the maximum possible cardinality of a hyperplane section is given by the cardinality of the Grassmannian over fq minus q to the power delta, and the number of hyperplanes which attain that is this. Okay, so I should say that this result was known for small l and m by two brothers called Ryan, C.T. Ryan and K.M. Ryan, who for small values of l and m actually first studied this. But for the general case, Nogin was the first one to prove this. And at some point of time, I became excited about that result, and I was trying to do something else. And but then Nogin, in fact, found not only the minimum distance, he actually found the generalized Hamming weight for certain values of R. Remember, this R goes from 1 to k. K was the dimension of the code, which is m choose L. So what he showed, not for 1 less equal R less equal m choose L, but up to a rather small quantity, I will denote it by mu, 1 plus the maximum of L and M minus L. He showed that well, R equal to 1, it is Q to the delta, R equal to 2, it is Q to the delta plus Q to the delta minus 1, and so on up to Q to the delta minus R plus 1. Okay, as long as R is less than or equal to this quantity mu. Typically, this mu would be much smaller than M choose L. M choose L is roughly of order M to the power N, where this is maybe of order, M or M minus N. So, but nonetheless, you have that. And one of the first results proved was with the Jill Lasho. We gave alternative proofs of this using some kind of combinatorial object called closed families and so on and so forth, and a certain structure theorem, whose very, very special case is the following, that if you look at a simple graph in which any two edges are incident, that means they have a vertex in common, then this graph is very special. This can either be a star, like with one vertex in the middle and the edges emanating out of that, or a triangle. Okay, you see that any two edges are incident, and if you require that any two edges are incident, then it has to be this kind of a graph. But what we sort of did was to prove an analog of this for uniform hypergraphs, and this helped in getting this, for instance. Okay, I said already that this number is usually much smaller than K, and so it doesn't give all the higher weights. Okay, but this is as you can see, this is a pretty old result, 25 years ago. In fact, Nogin's is even older than that. Okay, so 30 years ago almost. Okay, very good. So let's continue. So I'm just repeating the result that I showed you. The R generalized Hamming weight up to this quantity mu is given by this formula. So you should think of it as the first few generalized Hamming weights are given by this formula. Those of you who know coding theory may be interested to know that this is what is called the Grismer way bound for the generalized Hamming weight. So up to this value, the codes meet the Grismer way bound. Then several years later, these Scandinavians, Johan Hansen, Trygve Johnson, and Christian Randstad, they showed that, well, just like the first few, the last few generalized Hamming weights are also easy to find. And so this is like D1, D2 up to D mu, and this is from the other end dk minus 1 up to dk minus mu. So it's actually, dk of course is n because the code is non-degenerate, but dk minus 1 would be n minus 1 and dk minus 2 would be n minus 1 plus q and so on. So every time you want to calculate dk minus r, they say you subtract the cardinality of projective space of dimension r minus 1. And then this is, so roughly speaking, what this says is that the sum of the terminal higher weights or terminal generalized Hamming weights. And this says that some of the initial generalized Hamming weights. Actually, it turns out that this result is somewhat simpler than this, but somehow nobody had explicitly observed it until then. So they pointed this out. And nonetheless, there is a gap. Okay, so what do we do there? So let's try to understand this gap. Okay, so let's look at some examples. Suppose I take L equal to 2 and M is equal to 5. So K will be phi choose 2, which is 10, and mu will be 1 plus maximum of L and M minus L. So that would be 1 plus 3, which is 4. So Nogin, etc. would give us D1 to D4, and the Scandinavians, Hansen, Johnson, Randstad would give us 10 minus 4, which is 6, so D6 to D10. So here we don't know what is D phi. Whereas this gap will become wider. Suppose M equal to 6, L is still 2, then K is 15, 6 choose 2, whereas mu is 6 minus 2 plus 1, so that's 5. So in this case, we would know D1 to D5 and D10 to D15, but we don't know D6 to D9. Okay, so in general, if L equal to 2, you don't know DR when R is between M and M minus 1 choose 2. Okay, so to partly remedy that, what Hansen, Johnson, Randstad did was to actually find this missing, the single one in this particular case, D5, using some clever algebraic geometry. So they showed that, remember, D1 to D4, this would be Q to the power delta. Here delta would be L into M minus L, so 2 into 3, that's 6. So Q to the 6, then the next one is Q to the 6 plus Q to the 5, and so on. D4 would be Q to the 6 plus Q to the 5 plus Q to the 4 plus Q cube. And you might expect that maybe the one after that is you add a Q square, but that's not what happens. What they showed was you have to add a q to the power 4. Okay, so that's the pattern changes there. And they showed that this d phi is given by this formula, that you add q to the power 4. And they also made a conjecture that this is always a power of q, the difference between any two consecutive. And okay, so I would say in retrospect, in fact, proving this is actually much harder than proving this result. Oh, sorry, this is a different one. Okay. I'm sorry. Yeah, then proving this one. This is, once you get the correct hang of it, it's not so difficult. So it's a beautiful proof actually to show this. So I became interested in this, and what we did was again, this is an old result with Patil and Pillai, who was my former student and a colleague. We showed that this sort of a pattern happens at the next step always when L is equal to 2. So you have this mu. Yeah. Yeah. Previous slide. This one? Yeah. Which one? Yeah. Positive. Yeah. In some sense, what is sort of the game is happening if you think of the Gaussian binomial coefficient, it turns out that every time you are adding one of the powers, so that at the end you will get n, which is the full Gaussian binomial coefficient. But which power you add at which stage is kind of an interesting combinatorial question. No, I mean it is okay. What we always know is that this is always positive. Okay, but of course it's not obvious that it is a positive or non-negative power of q. Let me say non-negative because in some cases you might add 1. Okay, sure. So I was saying, so we kind of generalize this thing for C2 phi, or what they had, by showing that if L is equal to 2 and M is arbitrary, and you can assume without loss of generality that M is at least 4, then this mu will become M minus 1, and so for the mu plus 1, it's always adding q to the power delta minus 2. So there it was q to the power 6 minus 2 was 4, and whereas this is one more from the initial sequence, and we had the similar result where you extend the Hansen-Johnson-Randstad by adding, you subtracting not the power this cardinality of this mu dimensional projective space, but also subtract q square. Okay, and of course you get C2 phi, and this proof was kind of nice because it used what I think of as an algebraic analog of this structure theorem for closed families, which later I realize is kind of known in some literature, but we proved it for ourselves. So the question is the following, that suppose you take this exterior power and you look at subspaces of this. You want to ask what are the subspaces for which every non-zero element is decomposable. That means it's like V1 wedge, V2 wedge, Vn. In general, things are a sum of those things, right? And what's the maximum possible dimension of such a subspace and so on. Okay, very good. So let me just move forward in years. Now we know many more things about the Grassmannians. So for example, we know what is the automorphism group, and the automorphism group is sort of very interesting. It's like a certain subgroup of this general linear group on M choose L cross M choose L matrices, or general linear group on wedge L of V. And in the classical literature, I don't know if people are familiar with what is called the Lth compound of a matrix. So this is what it is. You take a M cross M matrix, and L is any number between 1 and M. Now you take all L cross L minors. How do you pick L cross L minors? You pick L rows, you pick L columns. So L rows you can pick in M choose L ways, L columns you can pick in M choose L ways. So for any choices of say alpha and beta of L rows, L columns, you get a submatrix and you take its determinant. So now you put this determinant as an alpha beta entry of a huge matrix, M choose L cross M choose L matrix. That matrix in classical literature is called the Lth compound. Those of you who like matrices and determinant, a good exercise is to calculate the determinant of this huge matrix in terms of determinant of the original matrix. That's called Sylvester-Frank identity. But anyway, so you sort of think of Lth compounds, and And okay. And together with, you have to take a symmetric product with together and non-singular scalar matrices. And but somehow there is a special case if M is 2 times L, then you also have to take a symmetric product with Z mod 2Z or Z mod 2Z. I don't know if you say Z or Z here. Yeah. That's slightly technical, but okay, maybe I will explain to you later. But there is a certain twist which only comes into the picture if M is equal to 2 times L. Really speaking, if you know geometry, this goes back to a classical theorem of Chow about automorphism of Grassmannians. And but then you have to adapt it to the finite field situation. So this is the old result with Krishna Kappa that I proved. Then Peter Bielan from Copenhagen and Fernando Pinheiro, who was sort of his PhD student, and also that of Tom Holt, showed that the dual minimum distance is very small. So this, remember, this is like a LDPC thing. The dual of the Grassmann code has minimum distance 3, and they have a beautiful characterization of what are the minimum weight code words of the dual. They said that something is a minimum weight code word if you're only their support, which would be kind of indexed by points in GLM, sort of lies inside a line in the Grassmannian. And moreover, the dual is generated by its minimum weight code word. So it's like a regular LDPC code. Then there was an interest in decoding. Peter Bielan and my former student Prashant Singh, they gave a very nice decoding algorithm for the Grassmann code, which can asymptotically correct, well, not d over 2, that's always the ideal, but d over 2 to the power L plus 1 errors, where d is the minimum distance. And somewhat recently, they could achieve the holy grails of d over 2 approximately errors. So that's a very good decoding algorithm when L is equal to 2. So point I'm trying to make is that this results kind of show you that Grassmann codes meet several of the requirements I put down for a good code. Okay, very good. How much time do I have? Are you bored or 15 minutes? Okay, thank you. You're very generous. We lost some time for technical things, right? Yeah, very good. Okay, so now that's the story of Grassmann codes. I want to turn to Schubert codes. So Schubert codes, because of a certain conference in Mexico, were introduced by Jill Lashu and myself way back in the paper where we gave alternative proofs of Nogin's results on generalized Hamming weight. And what are Schubert codes? So I already defined what they are. And we wanted to find a formula for their minimum distance exactly like Nogin did. Nogin showed that q to the power delta is the minimum distance for Grassmann code. A beautiful proof. But what we could show at the time was that the minimum distance is always bounded above by q to the power this quantity delta sub alpha. What is delta sub alpha? It is summation alpha I minus I. Just notice that if alpha were that maximal element in the Bruha order, which means m minus L plus 1 to m, which means alpha is m minus L plus I, then if you subtract I, you just have m minus L as every summand, and this will become L times m minus L. In other words, this is delta. Okay, so if alpha is the maximal element, in which case the Schubert code is the Grassmann code, this is exactly q to the power delta. In general, this number is precisely the dimension of the Schubert variety, if you think of it as an algebraic variety over, say, classical algebraically closed field, if you like. Okay, so we conjectured, in fact, for various reasons, it seemed natural that the minimum distance is in fact given exactly by q to the power delta alpha. This, I call this minimum distance conjecture, and what we proved here is that it is always less equal this quantity. So, okay. So that was, and of course this is true if alpha is the maximal element. And this actually generated a lot of interest among people. As I told you, maybe I will ask you, you can ask me during questions. There is a Mexico connection to this result and this conjecture. So people became interested in that conjecture, but then also they were not sure, remember for Grassmann codes, I wrote the length and dimension very explicitly. I said that the length is the Gaussian binomial, dimension is the ordinary binomial. Whereas for Schubert, I didn't really tell you, I just said n alpha, which is the number of FQ rational points of Schubert variety. But what is it explicitly? Do I have a nice formula? And I didn't tell you about the dimension k alpha, I just said it is the number of betas for which beta is less than or equal to alpha. So one of the things people tried to do was to not only look at this conjecture, but also try to calculate the length and dimension explicitly. So what they showed, so the first set of results was by Hao Chen, a Chinese mathematician. I think he was visiting Sticktenot at the time. So he showed that if L is equal to 2, and then you can actually assume without loss of generality that alpha is something which ends in M, then the length n alpha is given by this formula. Okay, it's rather explicit, of course, not very compact. And the dimension is given by, if the first coordinate is m minus into parenthesis h plus 1, then it is given by m choose 2 minus h plus 1 choose 2. Okay, and Rita Vincenti, who was in Perugia, Italy, she actually gave a formula for n alpha in general. It's a complicated formula. It's a summation over multi-indices and the product of Gaussian binomial coefficients times certain power of q, and this Gaussian binomial have this alpha I plus 1 minus alpha I over ki plus 1 minus ki multiplied by this power, where the sum is over all L minus 1 tuples k1 to kl minus 1, which are ki is between I and alpha I, okay, and ki is less than or equal to ki plus 1, and of course because I have ki plus 1, I should tell you what is k sub L and k sub 0, so those are the standard convention. K0 is 0 and kl is likewise alpha 0 is 0. Okay, so anyway, complicated, yeah. Yeah, good question. Well, it's not a meaning so much in coding theory. Generally speaking, when you're looking at subspaces of a finite dimensional vector space over a finite field, when q goes to 1, that roughly speaking corresponds to subsets of a finite set. It's just like, this is sort of a philosophical way of looking at that limiting formula. Limit of the Gaussian binomial is the ordinary binomial. M choose L is the number of L element subsets of 1 to M. So you should think of q goes to 1 as doing subspaces, etc., over a field with one element. But of course, if you talk about field with one element and you have professor of algebra, they'll say there's no such thing as a field with one element. Although I know that there are people who do algebraic geometry over F1 and so on and so forth. But so that's, Rota wrote a very nice paper on subsets and subspaces where he explains this analogy in great detail. But that's how, so it's not so much a coding theoretic meaning, but if you like, a combinatorial meaning. So since you mentioned, so we can sort of go back to the d upon n for Grassmann codes or Schubert codes, in fact, then you will see that and k upon n. K upon n would be m choose L over the Gaussian m choose L. So the limit of that as q goes to 1 will be 1. Whereas the limit of the relative distance q to the delta over the Gaussian binomial, that limit would be 1, but as q goes to infinity. Because you have a polynomial, monic polynomial in q of degree delta in the denominator, and you have q to the delta in the numerator. So asymptotically they are of the same order. As q goes to infinity, the limit will be 1. Right? So that's very nice illustration of why these requirements are conflicting. Rate becomes good if q is small, whereas the relative distance becomes good if q is big. Right? Okay. Okay, so then, so I should, of course, I will come back to the minimum distance conjecture, but then Misha Fassmann and I got interested in these works, and about finding length and minimum distance, and we realized that actually the problem was solved, I don't know, maybe 70 years ago, essentially in an old classical work of Resumen, in a paper in 1934 in the Annals of Math, where he gives what is called a cellular decomposition of the Grassmannian and the corresponding thing for Schubert varieties. Of course, Resumen works over complex numbers, but the same ideas will actually show that the length of any Schubert code is always given by this formula, summation q to the power delta beta, where beta is over all L tuples of positive integers strictly increasing, so that beta less equal alpha in the Bruch order. That means beta I less equal alpha I for each I. So that's a nice simple formula. Of course, the complexity is hidden in the summation, but nonetheless. But then, of course, even when alpha is the maximal thing, this is a complicated expression, unlike the Gaussian binomial, which is a closed form. So we wanted to get something like that, and then we sort of have this formula which is ugly or beautiful depending on your viewpoint. So we said that n alpha is given by, this is somewhat Vincentti-like formula, but more, so suppose it has u plus 1 consecutive blocks. That means, let's say, alpha 1, alpha 2 sort of start being consecutive up to a while, then there is a jump, and so on. So if it is the full Grassmannian, it's just fully consecutive. So suppose you have u plus 1 consecutive blocks, then it's given by this kind of a product involving a function, which sort of comes from the Mobius inversion in the classical algebraic combinatorics, which is given by this. This is slightly complicated, but I just want to point out that if you were to specialize it to the case of Grassmannians, you would get back the Gaussian binomial coefficient. So it has much fewer terms because the number of consecutive blocks usually will be much more. Because when alpha is fully consecutive, u is equal to 0. It's just, so this product is 1 and so on and so forth. This becomes much simpler. Okay. There is a third formula which unfortunately I have not published. It's an unpublished result of mine with Christian Kratenthaler from Vienna, and where we showed that this n alpha is given by the determinant of a L cross L matrix whose entries are certain products of Gaussian binomial times certain powers of Q. Okay. This comes by exploiting connection with what are called plane partitions and McMahon's formula and such things. But so it's a very nice explicit formula. And again, if it is consecutive, then it's much simpler. Okay, so point is, you know the length of this Schubert code explicitly for any alpha. And this is, yeah. Then what about the dimension? So as I was saying, the length was essentially known 70 years ago. The dimension, I realized, was also known about 60 years ago. And the reason it is known is because 60 years ago, Hodge proved what is called a postulation formula for Schubert varieties in Grassmannian, which explicitly speaking, which in a way gives you the Hilbert function and the Hilbert polynomial of the Schubert variety. So if you sort of look at that and you do some specialization, then you can get a beautiful formula for the dimension. In general, this number k alpha is actually given by a L cross L determinant whose entries are binomial coefficients. So this is a binomial determinant, and it's a little bit explicitly like this. Unfortunately, it is not a triangular matrix, so the determinant is not so easy to evaluate. You have one on the super diagonal, but and in fact it is easy to evaluate. For example, if alphas are in an arithmetic progression, in particular consecutive, then it's given by a much simpler thing like this. Or you can sort of force an expansion and you would get some formula like this. But I prefer this binomial determinant formula. So anyway, the point is, you know the dimension explicitly, you know the length explicitly for any alpha, and that's what Misha Fassman and I proved again long ago. Okay, now what about the minimum distance conjecture? So I had some pauses and so on, but I just removed them. So anyway, so recall what was the minimum distance conjecture? Or the minimum distance of Schubert code is given by q to the power delta alpha, where delta alpha is summation alpha I minus I. And already if alpha is this maximal element, the work of Nogin tells you that this is correct. If L equal to 2, this was proved by Hao Chen, who not only calculated the length and dimension, but proved this conjecture for L equal to 2. And independently, Lucio Guerra and Rita Vincentti, they also gave another proof of this. In fact, without realizing this at the time. And they gave also a lower bound in general for the minimum distance. Remember my old result with Lashu gave an upper bound, it's q to the power delta alpha. And the lower bound is roughly of order q to the delta alpha minus a. More explicitly, it is this quantity. And then they looked at Rita Vincentti looked at a special case of Schubert varieties, where you take the simplest Grassmannian, simplest non-trivial Grassmannian, which is not a projective space, J24, and you look at this sort of simplest non-trivial Schubert variety in that, the so-called Schubert divisor. This in finite geometry is called Klein quadric, and there they showed that the conjecture is correct. And then Fassmann and I, we showed that this is not just true here, but always true for any Schubert divisor. So Schubert divisor is a co-dimension one Schubert subvariety of Grassmannian. So we proved, in addition to showing that length and dimension, we showed that it is true. Eventually, it was stated, I think, in 1998 or published in 2000. Some 10 years later, Chinese mathematician Professor Xiang proved that the conjecture is true in general. So we know the, except that maybe the paper is not so easy to read. If you look at the Math Science review, you might. So I thought it should have a nice, more streamlined proof. Another 10 years later, with a former student, Prashant Singh, and I, we also gave an alternative proof of the general conjecture. So at any rate, we know the minimum distance now. So the minimum distance conjecture is proved. Okay. So of course, when you solve one problem, you want to ask for more. So I wanted to up the ante. So one conjecture is proved. So then we wanted to look at what are the minimum weight code words. That's another natural question. Okay, so you know the minimum distance, but what are the elements of the Schubert code for which the minimum distance, minimum Hamming weight, for which the Hamming weight is exactly the minimum distance. So we started to understand that, and remember this was characterized also by Nogin in the case of Grassmann codes. So what we did then, we started understanding it, and in the case of Grassmannian, what happens if you see the minimum weight code words exactly correspond to the decomposable element of this dual of Wage LV. Okay, so now we ask whether this is true in general, whether for the Schubert code, is it true that every decomposable element corresponds to a minimum weight code? And it turns out that the answer is not no in general. There are things which are decomposable. So I just take an example with L equal to 2 here. Let me not get into the details, but unfortunately the answer is not as simplistic as it was in the case of Grassmann code. It's not quite true that the decomposable elements give you the minimum weight code words. And for example, in this particular example, here I am taking a decomposable element in wedge M minus L, which is L is equal to 2, E3 wedge EM, and look at the corresponding code word. And then you can show that the Hamming weight is given by this formula, and it will coincide with the q to the power delta alpha exactly when alpha 2 and alpha 1 are consecutive. That means alpha 2 is alpha 1 plus 1, which is really the case when the Schubert variety is like a Grassmannian. Okay. So on the other hand, there are decomposable elements, not this, but for example this, where the minimum, the corresponding code word has the correct minimum weight. So it was sort of a challenge as to understand what are the elements, let's say here in this space, which give me minimum weight code word. So some decomposable seem to work, but not every decomposable work. So we kept thinking about this, and so we came up with what we thought was the right notion. So I like to call this notion of a Schubert decomposable element. So let me try to explain what is this. So what you do is, so you take in your parameter space, if you like, an element f wedge M minus LV. Let's start with a decomposable element. That means it is something like F1 wedge, F2 wedge, Fm minus L, where Fi's are linearly independent. Okay? I call this Schubert decomposable if in addition to being decomposable, it satisfies a certain dimension condition. Okay? Let me just remind you that in general you have, whenever you have an element in this exterior power, you have something called the annihilator, which is just a set of all elements in your vector space V, so that V wedge this element is 0. And to say that F is decomposable is exactly saying that this annihilator has dimension M minus L. And these Fi's will then be a basis of the annihilator. That's an easy characterization of decomposable element. So what we say is that, of course, if it is decomposable, this will have dimension M minus L, but we want that its intersection with this AI, or A sub pi, now I'm sorry, I'm calling this AI as A sub pi, should be the correct dimension of sort of alpha pi minus pi. And this should happen for all I from 1 to u. Okay, so now what is u? So I come back here and explain what is u. So what is u is the number of the u corresponds to the consecutive blocks in the tuple alpha 1 to alpha L. So what you do is, I start with alpha, the next guy may be consecutive, alpha 1 plus 1, then alpha 1 plus 2, and so on. Maybe this happens up to alpha P1, and then there is a jump. That means the difference is 2 or more. And then it continues to be consecutive for a while, then there is a jump, and so on. So suppose you can write always alpha uniquely, so that these guys are consecutive, and then here is a jump. So that's okay. I should have said that also. And so since I wrote pi plus 1, etc., pu plus 1 by convention is L, because that's the last guy. So there are u plus 1 consecutive blocks. Okay, and in particular, if alpha is consecutive, that means that's if and only if u equal to 0. And the other extreme is, it's what I call there are L minus 1 consecutive blocks, or rather L consecutive blocks. Difference between any two successive ones is 2 or more, and I will call that completely non-consecutive. Okay, so anyway, so you have these jump points P1, P2, etc., Pu, and you take the space A sub Pi, intersect the annihilator with that, and it should have this dimension. If that happens, then I will call F to be Schubert decomposable. And then okay, so let me just okay, so I should have used some pauses, never mind. In fact, so we made a conjecture that the minimum weight code words of the Schubert code are those which precisely correspond to Schubert decomposable elements. So of course, if alpha is the maximal, this is u equal to 0, and then this dimension condition is no condition at all, because that is for I equal to, sorry, this dimension condition, yeah, here, that is only for I equal to 1 to u. So if u equal to 0, this is an empty set. I mean, it's vacuously true. Okay, so it's slightly technical, but we believe that that was the correct condition. So the minimum weight code words we said are precisely those which correspond to Schubert decomposable elements. And so anyway, so what is the evidence that we have for this conjecture? So we proved various results. I think this is still open, I would say. But what we proved is that one direction, that suppose an element here is Schubert decomposable, then the corresponding code word is always a minimum weight code word. So if something is Schubert decomposable, the corresponding code word is a minimum weight code word. So now you have to show the reverse direction. In the reverse direction, we proved the following results. We showed that if suppose you take a code word of the Schubert code, indexed by F, and if it is indexed by F and F happens to be decomposable, then it is Schubert decomposable. Okay? So in some sense, if you have these two results, what you need in order to prove this conjecture is that if something is a minimum weight code word, then it should be represented by some decomposable element. That's not obvious. Okay? In fact, if you show that, then you're done. Okay? See, one of the problems with Schubert codes is that the evaluation map which sends F to C sub F is not injective. So there are lots of different Fs which will give rise to the same code word. So there can be one which is decomposable, one which is not decomposable. So what we want is that if something is a minimum weight code word, so it comes from some F, then it should come from some F prime which is actually decomposable. If we show that, then you put it together with these two results, then you would have the conjecture. Okay, let me, I think I must be near my closing time, so let me just try to wrap up quickly. Another result we proved is that if alpha is completely non-consecutive, that was the other extreme, then the conjecture is true. Then it is minimum weight code word correspond to some decomposable ones. And if you sort of assume the code words, assume the conjecture if you like, then you get a formula for the number of minimum weight code words. This is a little bit of combinatorics, because in general what you have is that this is the formula for the code words corresponding to Schubert decomposable. So anyway, this capital P is some number which depends on alpha and those block things. So this was a paper published in 2018, and unfortunately the conjecture is still open. So recently I tried to revisit it with another PhD student called Abhijit Panja and with my former student Murmay Datta. And okay, so then what we showed is that it is true in some cases. So roughly speaking, we showed that this is again true for Schubert divisors and things which are like Schubert divisors, somewhat more general than that. Okay, this is slightly technical, so let me not, unless you can ask questions and I can come back to this. But I just want to say that, okay, so this just innocuous thing, which actually, as I was saying, has origins in Mexico, resulted in a lot of activity. And over the years, people also have looked at many variants of this. So, okay, these are some results we know for the Schubert divisors and objects somewhat like that. And there are various other variants of these Grassmann codes which people have looked at. For example, Hansen, Johnson, Ransted, and later Pinheiro looked at what are called Schubert union code, which are corresponding to unions of Schubert varieties, with Peter Whelan and Tom Holt, and later on with Mrunmayee Datta as well as Pinheiro and Singh looked at what are called affine Grassmann codes. Then people here in Mexico City, I know that they have looked at Lagrangian Grassmann codes, and there's also Ilaria Cardinali and Luca Guezzi in Italy, they have looked at that. And they have also looked at codes from what are called orthogonal Grassmannian. This corresponds to symplectic Grassmannian. And this is a very challenging class of codes corresponding to flag varieties. We know some results. We have some work, but it's not yet published. And most recently, people have looked at what are called higher Grassmann codes, which roughly speaking correspond to taking Grassmannian with its Plucker embedding, follow it up with a Veronese embedding, then you have Grassmannian sitting inside a very big projective space, and you look at the codes corresponding to that. Okay? Anyway, so I think I have probably exceeded my time, so thank you very much.
Are there some questions?
Thank you for your nice talk. There is any relation between the minimal distance of a code and its dual, at least for Grassmannian or Schubert codes, and for the other quantities you define?
Okay, so so I should have probably mentioned. So the minimum usually for these kind of codes which are given by non-degenerate projective algebraic varieties, the minimum distance of the dual is not so difficult to find. So there is no direct relationship between the minimum distance of a code and of its dual. It's not like you know one, then you have a formula which determines another. But there is a very beautiful relationship between the spectrum of a code, okay, and the spectrum of its dual. This is called Macwilliams identity. So I just see what you can do is, suppose you have a code, and then you look at, let's say, AI of C, which is the number of code words of Hamming weight I. Okay, and maybe one way to encode it is you write a two-variable homogeneous polynomial, summation that. This is called the weight enumerator polynomial of the code, WCXY, let us say. Okay, and you can write down a similar thing for C per for the dual. What is the minimum distance would correspond to? Here this I will go from 0 to n. So I equal to 0, that's just the 0 code word. So in some sense it's the first non-zero term here other than the constant term. Okay, that would be the minimum distance. Okay, so you have a relationship between this and the corresponding polynomial for C per. And this was proved by Florence J.C. Macwilliams, a very brilliant mathematician or electrical engineer perhaps, who she showed that, well, you can, I mean, I can even write down that relationship. Or you can just look up Macwilliams identity. But this other remark which I made was that we now understand that for codes like Grassmann or Schubert code, the minimum distance is not very difficult to find for the dual. Okay, and it will typically turn out to be, see what it has to do is whether the variety contains like a line or a projective space of dimension 2 or dimension 3, etc. In some sense, that is what is behind the formula for the last few generalized Hamming weights of the Grassmann codes, which Hansen, Johnson, Ransted obtained. Okay. So in both for Schubert and Grassmann code, we know actually that the dual minimum distance is 3. Except that for Grassmann codes, the dual is generated by the minimum weight code. This is not true in general for the Schubert code. Under some condition it is true, but let's say in general it is not true.
Another question?
Actually, it's a curiosity.
Yeah.
Is it not, what is the relationship between code theory and modular forms? Because many of the formulas that we're presenting, they appear in modular forms. But
Yeah.
there is another formulas which they're completely strange to me.
Okay, well, I'm not sure if I have a canonical answer to this, but see, in the, let's say about 20, 30 years ago, people in coding theory were very excited with the class of codes called Gopa codes, which roughly speaking come out of vector spaces, which are like the subspaces which will arise when you do Riemann-Roch theorem over a curve, right? So you have a divisor and you have the corresponding Riemann-Roch space, and then you can define an evaluation map and you can associate a code to that. And that's called a Gopa code. And what, in fact, Fassmann, Vladut, and Zink, they showed that if you looked at this Gopa code corresponding to elliptic modular curves, you get a class of codes which is particularly nice in it that it beats what is called the Gilbert-Warshaw bound. Actually, they showed it that this is true for q bigger equal 49. And then, so people have been associating codes to modular curves. In the later years, people like Elkis and so on have looked at Drinfeld modular curves and also looked at the codes. So there has been a lot of activity in that, which has this relationship. Of course, modular curves, etc., are closely related to modular form, and that way you have a connection. I know that you probably looked at the formula involving Q and you're sort of thinking of Q series identity or theta functions or I don't know what, but I do not know a straightforward relationship between that and some modular form. It would be interesting if you can help me understand that, maybe, or somebody else. You can help, okay. Yeah, it is. Yeah, I mean, yeah. It just sort of goes to show the more we know, the more we don't know.